author is Schlossnik, and also Kibble, Schlossnik, and this name should tell you something. They find also a bouncing universe, but they have partly in their work not only the curvature scalar, but they have also the term B0 times epsilon ijkl times r ijkl. In a Riemann-Cartan space, the totally antisymmetric piece of the curvature doesn't vanish, and they also consider such a piece. They also find a bounce. But in contrast, Friedrich, very known on nuclear physics, and Rudenko, they find only a very, very small addition of the spin contact interaction, and they argue that they cannot prevent a bounce, they cannot induce a bounce, no bounce. I mean, one should really look into these articles in detail, which I have no time to do that. And there is this is all 2030, and I just invite you to look at these papers, and perhaps when you may be interested to follow up one of these things. It's all 2013. It's in the archive of this will come out in Physical Review, and he finds that he can even, after the inflationary period in the preheating area, he can, after inflation, he can produce a condensation, a fermion condensate, which is produced by torsion. Fermion condensate. I just mentioned these things because I know people in Professor Deng's group are more interested in dark matter, dark energy, and also in such cosmological questions, and I think that the Einstein-Cartan theory can also contribute to a discussion of cosmological facts which are by far not yet exploited, and one should look much more in detail into these questions. But this is only the most simplest case theory of gravity theory, Einstein-Cartan theory, and even in this theory, things are not too clear yet with respect to cosmology. I'm sorry. Thank you very much.
Could you tell us more about the kind of idea of how that connected to the inflationary scale?
I don't know. Okay. I mean, I discussed it with him. I forgot part of this discussion, and I'm not really. He has not provided a preprint of this work, and I only heard an oral presentation. He just looked into these fluctuations in the CPM and found that if he sort of calculates whatever he can calculate and extrapolates back, then the earliest things where he can really make reliable statements are of the order of 10 to the minus 27, he said. And he said centimeters, and he said in his talk, we can now test general relativity up to 10 to the minus 27 centimeters. And I told him, have you looked into the Einstein-Cartan theory? No, he hasn't. So perhaps one should try.
So he gave a seminar on this.
In Bonn, yes, it was a colloquium. It was a colloquium in Bonn 3 months ago or something.
I guess he is the major person who made the now the standard theory of quantum fluctuation induce everything now.
He is at least the main contributor to all these things. And I found it interesting because I just looked into this question of the Einstein-Cartan theory because of our book. Most of what I did in this theory was 30 years ago, but in composing that book, I looked into some of these old questions. I'm sorry, I'm a little cold. And then I saw that when Mukhanov gave his talk, it's exactly borderline between Einstein's theory and Einstein-Cartan theory, where he believes that he can make reliable statements. And I quote from a letter, it should be inquired if somebody is looking for an interesting subject. This is so very interesting subject.
Yeah, and also he will write an article for the Centennial volume.
Mukhanov.
Yes. It's mainly about fluctuation in use.
Okay.
But he may mention that because it's all related to also to time.
Yes. Yes. These people usually believe in Einstein's theory, not because.
But it's okay to the inflation period. I mean,
okay.
It's quite far.
I'm just saying that's a subject worth of investigation, taking into consideration these new results of these people and making a coherent view out of it. This is what somebody wants to go into that subject.
Any other questions? Okay, so now let's thank Professor Hehl again.